Number 19. If 13 cards are randomly chosen without replacement from an ordinary 52 card deck, what is the probability of obtaining exactly 3 aces? Exam 3, problem number 19. We want to find the probability of obtaining exactly 3 aces, where that's the classic hypergeometric distribution. And here's the solution. There's 4 aces, we're choosing 3. There's 48 other cards, we're choosing 10, and it's over 52 choose 3. Number 20, let x and y be random variables with the joint density function of f of xy equal to e to the minus x. That x goes from 0 to infinity, y goes from 0 to 1. If z equals x plus y, 2y, then where the joint density function of x and z is non-zero, which of the following is true? Number 20, we want to find the joint density of z and x, and then figure out which ones of the following solutions are true. And now I give 2 different possibilities for solutions for this. And so we'll go through them. So here, this is our joint density, and we're interested in z, which is x plus 2y, and x, which I'm just going to call w to make my notation a little easier. So we're going from xy space, which is R2, and we have to map to R2. And when we do that, we set it up like this. So the Jacobian of the transformation is 1/2. So the joint density for f of wz is f of xy with then x and y of these values plugged into the joint density times the absolute value of the Jacobian, and we get 1/2 e to the minus w. So now the first possible solution is this. So if you look at the joint density, and x is from 0 to infinity and y is from 0 to 1, you can take the joint density, which is here, and if we multiply it by 1, that looks like the product of 2 marginals, and it is. And so since the joint distribution can be broken up into the product of their marginals, that's the statistical definition of independent. So x and y are independent. And notice that functions of independent variables are also independent. So x is independent of 2y. Okay. Now this argument here of splitting them up, you can, with more practice, you can just see that. But if needed, then you can take the joint density and find the marginals by integrating out the other values. So if you want to find the marginal of f of x, you can integrate out y, and you do get e to the minus x. And then to find f of y, you integrate out x, and you get 1. And so then 1 times f of y times f of x is the joint density. So that's another way to do it. So now if you notice that x is not independent of itself, that's just a fact, but you can write x as z minus 2y. So now we know x is independent of y, but we know that x and x aren't independent, and so we know that x is not independent of this quantity, so it must not be independent of z. So x is not independent of z. Okay, so that's one possible solution. That's sort of a heuristic argument to find the solution here. So the second one involves a little more calculus here. So let's go through it this way. So here is our domain of our original x and y. It's a rectangular region from 0 to infinity and 0 to 1. And then this maps to this region here, this whatever that region's called. So and this is important when we're integrating out the joint density. Now we found the joint density for w and z up here. So the joint density of W and Z is 1/2 e to the W. So now to integrate out and just find the density of F of W, then we have to use this region here. So we're integrating out Z, and Z goes from W plus 2 to W. That's the limits of integration, and then we get e to the minus W. Now to find the density of F of Z is a little bit trickier, because when we integrate out W, we need to split it up into regions. If we go from Z equal W to Z equals 0, but then once you get past 2, you have to integrate from those two lines. So you have to set it up as two different regions, two different densities. And so if you integrate out, and then from 0 to 2 you get this, from 2 to infinity you get this, which clearly the product of F of Z and F of W does not get our joint density back. So they're dependent. So the answer is A. Number 21, let X bar be the mean of a random sample of size 4 from a normal population with mean mu equal to 1 and variance equal to 16. What is the probability that the absolute value of X bar minus 2 is greater than or equal to 2? So number 21, we want to find the probability of the absolute value of X minus 2 is greater than or equal to 2. Well, the definition of absolute value being greater than some constant means you can split it up into values greater than 2 and values less than 2, minus 2. Well, here then you take the 2 to both sides, you get X bars greater than 4, X bars less than 0. But now if we transform this to a standard normal, because we're given that X is from a normal distribution, so X bar is distributed normally, so we can transform it to a Z, or the standard normal distribution. So we subtract the mean and divide by the standard deviations to both sides, and that's a Z variable, which then we can look up into the cumulative Z tables in our book. We get these values, and that's the answer. Number 22, let X be the number of successes in a fixed number of repeated trials, and let P be the probability of success in any one trial. If the mean and the standard deviation of X are equal, which of the following values could be equal to P? So number 22 is we want to find, we're given that X is binomial, and the mean and the variance of a binomial are these values, and we're given that the mean is equal to the standard deviations, and then we want to find the possible P values that satisfy this. Well, to solve this, we're also going to solve it two different ways. You square both sides. N squared P squared is equal to NPQ, which is 1 minus P. And then that implies this equation. So you have the number of you have two numbers times each other equaling 0. So their products one of those or both of them must be 0. So P equals 0 is a possible solution, but that's not a possible answer. So that's not it. So let's look at this piece here. So now one solution is that we solve for P, and we get P equal to 1 over n plus 1. Now what we do is we cycle through possible n values. So when n is 1, P is a half, and that's not a solution. When n is 2, P is 1/3. When n is 3, P is 1/4. And notice that the P's keep going down, and if we look at the answers, eventually when we plug in n equal 9, we get P equal to 1 over 10, which is 0.1, which is a solution. So another possible way to think about this is we were given this, we reduced it down to this equation, but if we solve for n, so n equals 1 minus P over P, and n must be an integer. So if we put the possible p-values back into this equation, it must be an integer. And once you start plugging values in, the only one that works is p equal to 0.1 to get an integer. And so that's the solution. Number 23, let x1 through xn be a random sample from a distribution with probability xi equal to 1 minus probability xi equal to 0 equal to a half. If y1 is the minimum of x1 through xn and yn is the maximum of x1 through xn, what is the probability that y equals 0 and yn equal to 1? So number 23, we want to find the probability that y1 is equal to 0 and yn is equal to 1, where y1 is the minimum, yn is the maximum. So one thing to note is that we look at, and our samples only take on values of 0, 1. So if we look at all the possibilities that y1 and yn can take on, that sample space has to be 1. So y1 0, yn 1, both of them 0, y1 1 and yn 0. Well, the minimum can't be bigger than the maximum, so that is 0, and both of them be 1. So this equals to 1. We don't know this, that's what we're trying to find. So both of them being 0 means every observation has to be 0. So that, and the probability to be 0 is a half, so that's half raised to the n. This is 0. All the sample space has to be 1, so that's 1/2 to the n. We can move these to the other side, and we get 1 minus 2 to the 1/2 n. But then that 2 reduces with one of those, so the probability is 1 minus 1/2 raised to the n minus 1. Problem number 24. A box contains 10 chips, theta of which are white. The null hypothesis that theta equals to 3 is tested by drawing 2 chips at random and without replacement. The hypothesis is rejected in favor of the alternative hypothesis that theta is greater than 3 if both chips are white. What is the significance level of the test? So number 24, we have, if we let x be the number of white balls, and we want to find and they give us the rejection that if both chips that are drawn are 2 or greater than 2, that's the rejection region. But since we're only drawing 2, that's the same as the probability that x equals 2. Well, this is the classic hypergeometric setting. So we have the null hypothesis is that theta is 3, so there's theta, if there are 3 white balls, we want to choose 2 times the 7 remaining, we want to choose 0, and that's over 10, choose 2. That reduces to 1/15, so that's the answer. Number 25. The random variables u and v are independent and normally distributed with mean 0 and 2 respectively. Each variable has a standard deviation of 2. Which of the following is closest to the probability of u being less than v? So problem 25, we want to find the probability that u is less than v. But let's subtract the v to this side, so the probability that u minus v is less than 0. So we're giving that u and v are independent normally distributed variables. So a linear combination of normal variables is normal. So we know that this is normally distributed. And so if we look at the expected value of u minus v, that expected value u is 0 minus expected value v is minus 2. The variance of u minus z is the sum of their individual variances, which is 4 and 8. So the variance of this difference is 8. So now we can use that to subtract the mean from both sides and divide by the standard deviation of both sides, and that transforms it to a z. So z is less than minus 2 over the square root of 8, which reduces to z less than minus 0.7, which you look in the back of the book to get 0.7580. Number 26. A model suggests that the mutually exclusive and exhaustive events A0, A1, A2, and A3 have probabilities given by probability of AK equal to this equation. The hypothesis that P is equal to 1/2 is to be tested using a chi-square goodness of fit statistic. The experiment is repeated 80 independent times, and the respective frequencies of A0 through A3 are 15, 25, 35, and 5. What are the values of the chi-square statistic and the degrees of freedom, respectively? So problem 26, we're given 4 mutually exclusive regions and exhaustive. And we're given a probability distribution function for those. So we can find out the individual probabilities of A0 is 1/8, A1 is 3/8, probability A2 is 3/8, A3 is 1/8. And we want to test the hypothesis of this. So there's 80 observations, and we find out how many fall into each region. So xi is our observation, that's our data. So the 15, 25, 35, and 5. And then this is what we expect. So if there are 80 observations, and the probability being A0 is 1/8, so we'd expect 10 observations in here, but we saw 15. And here we'd expect 30. So out of the 80, we expect 3/8 of them to be in region A1, and the same for A2 and A3. So now the chi-squared statistic is, it's the observed minus the expected squared divided by the expected for each category. Now those, on the test day, you can, you can quickly learn that this and this value is the same and this value is the same. Because it's 5 squared over 30, 5 squared over 30, 5 squared over 10. So you can calculate each of those. You get 6.6 repeating. On something kind of interesting, that repeating bar, its math name is called a vinculum. The degrees of freedom is K minus 1. Here there's 4 categories minus 1, so the degrees of freedom is 3.